In our last part on our discussion of low mass stars, we're going to bring up the idea of novas. Normally, a low mass star by itself is not massive enough to have a supernova occur, but there is a sequence that we can go through of what's a binary star system that allows for novas or type 1a supernovas. So let's go through the process. For starters, we have a binary star system. And by binary star, we're just saying two stars. And I'm going to label one primary and the other one a secondary star. What matters is that the primary star is just more massive than its companion. That's all it is. One star is, by definition, it's going to be more massive than the other. So, the more massive you are, the quicker you go through your stellar lifespan. So the more massive star will turn into a red giant first. This one will be a red giant, while the other one's still a main sequence star. And keep going through the chain. The red giant will eventually turn into a white dwarf, while the other one is somewhere on its phase between a main sequence or a red giant, somewhere in that phase. So the primary star has reached white dwarf status, whereas the secondary is somewhere earlier in its lifespan, between main sequence and red giants. And now this is where a fascinating game, a little interplay of matter starts to happen. The red giant swells up in size. This is the secondary star. It swells up in size until it starts passing what we call the Roche lobe. This should remind you when we discuss tidal forces, the gravitational pull across something. If you cross a Roche lobe, your mass starts to get pulled apart. Well, that's exactly what happens between the red giant and the white dwarf. The red giant has swollen up in size and to the point that a lot of its gases start getting siphoned off onto the white dwarf. So now matter from the secondary star is being dumped onto the white dwarf. And two things can happen. That white dwarf can either nova or a type 1a supernova. Nova. What do I mean by that? So what's happening? The red giant is dumping matter onto the white dwarf. And that's creating this dense and shallow atmosphere. And if things and conditions are right, nuclear reactions can literally ignite in the atmosphere around this white dwarf. And so for a few hours, the luminosity of that white dwarf will be upwards of 500,000 times the luminosity of the sun. Because think about it, it's as if we've detonated all of Earth's atmosphere into a giant sea of nuclear explosions. And that's happening across a white dwarf, which is even more massive and bigger than our planet. So the atmosphere of this white dwarf is suddenly this nuclear apocalypse blowing up, up, and up. And that matter gets distributed, thrown off, and this process could repeat for these binary stars. This red giant could swell up again, dump more matter onto this white dwarf, and create another chain reactions of these novas over and over again. Alternatively, the rate at which the red giant dumps matter on that white dwarf, it could be too great. What could happen is that the white dwarf reaches what's called the Chandra limit. Specifically, it's defined as a white dwarf of a mass of 1.4 solar masses. Property of objects of that size, if the white dwarf's mass suddenly became greater than 1.4 solar masses, something astonishing happens. Carbon suddenly ignites in the core of the white dwarf. Remember, way back when, the reason we said that all low mass stars become white dwarfs is because they're not massive enough. But because of this interplay of matter shifting from one to the other, all of a sudden that white dwarf has reached this critical level and carbon starts to fuse. And now it's as if we've ignited a switch. The fuse is detonated. The core of the white dwarf starts fusing, but it's an unstable reaction, and it creates this violent runaway effect that just starts exploding more and more and more until the entire star just blows up into this just gigantic supernova. The explosion itself can last anywhere from days to months. And the luminosity of that thing can be upwards to 100 billion times the luminosity of the sun. So recapping this process of this interplay of these stars. Remember, you've got two low mass stars in orbit, binary star system. The more massive one will become a red giant first, eventually turn into a white dwarf. And now we'll have this interplay where they shed off some layers of material, and then the secondary star, it starts turning into a red giant and dumping matter onto the primary, onto the white dwarf. So this interplay of one growing in age and eventually shedding off gases, that's on a scale of about 4 billion years. Then the spitting off of some atmospheric layers, hundreds of millions years. But then things speed up. This process of one star dumping its matter on the other, thousands of years. Not even millions, just thousands. And once that white dwarf reaches that critical stage, it can be a matter of seconds for the supernova to rupture, destroying the entirety of that star. So the white dwarf goes supernova. The companion, the red giant, it's gone. Probably still there, but impossible for us to see, because now all the debris of this white dwarf that went supernova is completely blocking our view of the universe. So here is the most recent supernova observed by the naked eye, called SN 1604, or more colloquially, Keplers Supernova. Yes, Johannes Kepler was watching the night sky and he thought he saw the birth of a new star, and that's what he described. It was so bright that people are actually able to look at this with just their naked eye, no telescopes necessary. And initially it was so bright that people were able to see it for weeks after the supernova had happened. For perspective, here it is today. It's about 25 light years in size. Right. When it went supernova, it had, by estimates, an apparent magnitude of minus 2.5. The planets in our solar system are not that bright. So this supernova, this star went supernova, and the explosion was so bright that we literally could see it for several weeks after that initial explosion. So to wrap everything up, remember, stars' mass determines everything. Its life, how quickly it burns things up, how big it becomes, what happens at its end. That is everything determined by the mass. One fact that I really want to emphasize here. The red giants, they are cooler stars. Red giants are cooler than their associated main sequence stars, but they are more luminous because of their size. They're able to radiate more photons per area. And because they swell up in size, yes, they are cooler, but they give off more photons. Eventually, the core of these low mass stars, they will start to burn helium. And it happens when the electron degeneracy pressure triggers that helium fusion. And then you can talk about all the different reactions of how that star reaches a asymptotic giant branch, grows up in size again, and eventually cools off, spits out all of its outer layers into nebula, and cools into a white dwarf. And all the low mass stars, if they're not a binary star, if they're by themselves, every low mass star turns into a white dwarf. So that's an end to a section 16, and everyone take care.